Our intuitive perception of winds does not cover all the properties of wind forces. In this post, we'll address some of the peculiar properties of wind forces that are counterintuitive and are related to the operation of Blackbird. We'll introduce the concepts of lift and drag, apparent wind, attack angles, and sailing against the wind. These concepts are the bread and butter of Blackbird theory. We usually think of winds as pushing forces. Winds push things that are on their way. However, quite often, winds also suck things into the airflow. It's easy to see it. Hold a piece of paper as shown in the picture. Now, blow above it, as shown in the right picture. The paper moves up. Your blown air did not push the paper, it passed over it. Yet, the paper was sucked by the wind. This kind of wind force is called lift force. When the air is blown directly into the paper, as shown here, the wind force pushes the paper in the wind's direction. This kind of wind force is called drag. When the air is blown as shown here, both the lift force and the drag force act on the paper. Their net effect is the total air force. In general, the lift force and the drag force are the components of the total air force. The total air force is stronger than each of its components. The direction of the total air force is in between the directions of the lift and the drag forces. All those air forces depend on the velocity and pattern of the airflow and on the shape of the object. In airplanes, the lift force points up. In sailboats, the lift force is horizontal. Let's examine now how wind forces act on airplanes. Both drag and lift forces act on airplanes. Consider an airplane taking off on a calm day. In order to take off, the airplane needs to attain a certain velocity, say 100 miles per hour. Its engine provides a thrust force that overcomes the drag force of the air and other opposing forces till the airplane reaches 100 miles per hour, and then the airplane is lifted by the lift force and takes off. However, the air was calm. There was no wind. What matters to the airplane is the apparent wind velocity, the velocity of the air as it appears to the airplane, the velocity of the air relative to the airplane. In this case, the apparent wind velocity was 100 miles per hour, and the airplane took off. Let's see now how the drag and lift forces change as the airplane runs on the runway in calm air. As the airplane's velocity increases due to the engine's thrust, the apparent air velocity increases. The two velocities have the same magnitudes and opposite direction. The drag and lift forces increase as the apparent air velocity increases. There comes a point that the lift force is slightly greater than the airplane's weight. That is when the airplane takes off. So far, we talked about calm air takeoffs. In those cases, the airplane velocity and the apparent wind velocity have the same magnitudes and opposite directions. This is not the case in windy takeoffs. Let's check those cases. Consider three identical airplanes. The first is taking off against a wind of 20 miles per hour. The second is taking off in calm air. And the third is taking off downwind, with a 20 miles per hour back wind. All three airplanes would take off at an apparent wind of 100 miles per hour. It turned out that the first airplane took off when its ground velocity was 80 miles per hour. The second took off when it reached 100 miles per hour. And the third took off only as it reached 120 miles per hour. Isn't that counterintuitive? It is a fact that airplanes need shorter runways when they take off against the wind. It is a fact that they need longer runways when they take off with the wind coming from their backs. Is wind helping airplanes or opposing them in takeoff? Let's see what is the explanation of this riddle. The solution of the riddle of the runways is that the lift and the drag forces depend directly only on the apparent wind. Not on the airplane's velocity, not on the wind true velocity. The latter two affect the apparent wind, but the apparent wind is what counts. This slide summarizes the results of those three airplanes graphically and verbally. It shows the relationships between the airplane's velocity, the true wind velocity, and the apparent wind velocity. Those relationships depend on the general situation. First, taking of in calm air. The airplane's velocity and the apparent wind velocity are equal in magnitude and opposite in direction. Second, taking off against a wind of 20 miles per hour. The apparent wind velocity is equal to the airplane's velocity plus the true wind velocity. 100 equals 80 plus 20. Third, taking off downwind. The apparent wind velocity equals the airplane's velocity minus the wind velocity. 100 equals 120 minus 20. And finally, when the airplane is not moving, the apparent wind velocity equals the true wind velocity. We will encounter all those situations when we deal with Blackbird. Airplanes fly due to the lift force generated by the airflow around their wings. The figure illustrates a simplified cross-section of an airplane's wing and the pattern of the airflow around it. In the following, we will call such a cross-section a profile. The wing splits the incoming airflow to two streams, one above and one below the wing. The two streams are formed at the same time and reconnect at the same time after passing the wing. Due to the wing's curvature, the upper stream has to travel a longer distance than the lower stream. It does it by moving faster. That difference in velocities creates an upwards lift force. The drag force is in the direction of the apparent wind. The total wind force that acts on the wing is the resultant of the drag and the lift forces. The total wind always points between the lift and the drag forces. One of the factors that affects the magnitudes of the drag and the lift forces is the angle of attack alpha, the angle between the direction of the apparent wind and the chord of the profile of the wing. Those effects could be grouped into four alpha regions. In regions A and B, the airflow lines are laminar, and the aerodynamic forces enable smooth flying. In region A, lift is the predominant force, and in region B, drag force is predominant. In region C, the airflow over the wing is turbulent, and the airplane stalls. In region D, the airplane loses its flying abilities. It drifts in the wind and may fall down. Similar situations occur also in sailboats. The difference is that sailboats sail also in region D. That is when they sail downwind. Usually, the range of alpha is between 0 in region A, when the apparent wind is in the direction of the chord of the profile, and 90 degrees in region D, when the apparent wind is perpendicular to the chord. The actual boundaries between those regions depend on the shape of the profile. During Blackbird's run, most profiles of the propeller experience apparent winds that are coming from all those alpha regions. Sailboats that sail against the wind is counterintuitive. The sails of those boats are of special shapes, and they are rigged in special ways. The boats used by Columbus and his contemporaries did not have those features. They had to wait for the appropriate trade winds in order to complete their round trips in the Atlantic Ocean. Let's see how sailing against the wind is accomplished. Let's compare two almost identical boats, except that the left one does not have a keel. The right one has a keel, the black center line. A keel is basically a flat blade sticking down into the water from a sailboat's bottom. One of the roles of a keel is to prevent the boat from skidding sidewise. Assume that the keel is ideal, so that the right boat cannot slide sidewise, while the left boat can slide in any direction. The boats are experiencing the same apparent wind, blue arrows, and their identical sails generate the same total wind forces. Red arrows. Now, let's see the two different paths that they take. The only horizontal force that was acting on the left boat was the total wind force. Therefore, the boat was pushed in the direction of that force. In the right boat, the reaction force of the keel, the black arrow, was acting in addition to the wind's total force. The total wind force had two components. One, the driving force in the keel's direction, pushed the boat forwards. The second component, the sidewise force, was perpendicular to the keel. This force was neutralized by the reaction force of the keel. As a result, the driving force pushed the boat diagonally into the wind. It looks like the boat is being sucked by the wind. The playlist Understanding Blackbird has more videos about this topic. If you like this presentation, please give us a like. If you would like to be notified about other posts of similar nature, please subscribe. Thank you.